We've been talking about how simulation can be used to drive innovation, so I'm going to show you what this looks like now in Star-CCM+. The example that I'm going to take is a Le Mans race car. We're going to start out by looking at a virtual prototype of this vehicle that's been built in the software. And we're going to use this to gain insight into the vehicle performance, both into the flow field and also into important numerical values such as drag and downforce. Next, we're going to generate and test a design variant. In this case, what we're going to do is we're going to move the rear wing. And we're going to have a look at what the impact is of this on the performance of the vehicle. This is a very quick and automatic process, and so we're going to do this together live in the software. Finally, I'm going to show you how automation of this change allows us to conduct an intelligent search of the design space in order to find the best possible rear wing configurations, for example for the track that you see in the top right of the screen. So far we've spoken today in fairly general terms about this concept of build, test, assess and explore. I'd like to go into that in a little bit more detail now in terms of Star-CCM+. So in building our digital twin, we start off by constructing or configuring our CAD, and we then discretize our flow domain to generate a volume mesh. The tests that we run are the solution of the flow solver, and of course we assess the outcome of those tests, carrying out various types of analysis in the flow field and on the numerical reports that are extracted. And after this, we're able to run this cycle as many times as we need in order to explore our design. I'm going to start in a moment by at the assessment phase in this loop, and we're going to have a look at the output of one simulation in Star-CCM+, after which I will make a change to the CAD to that positioning of the rear wing, and we will rebuild and retest the model, and you'll see how quick and automatic this is, and we will have a look at the comparison between the first and the second designs. Do remember though that although what I'm showing you is the manual process, our end goal here really is to run an automated search of our design space in order to intelligently find the best possible designs. So let's move into Star-CCM+. What we see here on the screen is our same Le Mans car, and we can see here a variety of different types of post-processing and analysis. Let's start here in the top left. What we're looking at here is the flow underneath the vehicle. You can see it comes in from the front of the car here at this end, and we can see we have a nice straight, fast-flowing flow coming under this flat bottom of the car. We see this very high speeds actually correspond in this pressure coefficient plot below to this nice area of low pressure that we have under the vehicle, which creates suction and therefore downforce for our car. We can also see as we move further down the car the formation of the wake, which starts, we can see here in this flow in the diffuser, and then if we just turn this around, we can start to see the wake shape behind the car here. So that's one way of looking at the wake. An alternative is to have a look at the total pressure coefficient, which is what we can see here in the top right. So I'm sweeping here through the car from front to back, and we're looking at that total pressure. This is quite similar to something you might do in a wind tunnel, where total pressure can also be measured. What we can see here though with CFD is that we're able to probe into any single point or any entire plane that we're interested in within our flow field, and we don't need to know in advance exactly what we might be interested in. If it's in our flow solution, then when it comes to our analysis stages, we're able to extract the information that we want. Here in the bottom right, you can see a line integral convolution plot. This is effectively similar to an oil flow plot in experimental terms. But what we see here is not only the direction of the flow on the surfaces, but we can also see the speed of the flow and where we have accelerations. One thing that we will be interested in is looking at the areas of very low flow speed and possible stagnation. And we can do that not just through the velocity, but also through a skim friction plot, which gives us very exact details on areas that might be of interest or concern. Some of these stagnation regions are expected, such as these bright green ones here at the front, but what we see here in the diffuser is not really what we're hoping for. We see that we have a separating or stagnant flow right here towards the rear of the car. This matches up with what we see in the pressure coefficient plot as well. We don't have as low pressures as we would expect or hope to see in the diffuser. And that, of course, corresponds to what we've seen here in our streamline plot, which is this circulating flow underneath the car. So that, in all, is something that we might well want to look into further. So that's some flow visualization, but let's have a think about some of the values that we might be interested in extracting as well. For ease of viewing, I've plotted some of these here in the bottom left. So we have our lift coefficient, which is a downforce, of course, our negative downforce. So we have a downforce on this vehicle, and we also have our drag coefficient. In addition, I've added the moment coefficient around the y-axis. So that's looking at the balance between the front and the rear of the car, i.e. are we going to get more grip on our front tyres or our rear tyres? That, in combination with our downforce information, is going to tell us whether we're likely to come off the track in a sharp corner, and really what we might need to look out for. So this is the behaviour of one design, but what we're really interested in is seeing whether we can improve this design. Can we make a better design? And to do this, we have to make a design change, and then we will compare the outputs from the two cases. So let's have a look at our geometry and think about making that change. Here we are then with the vehicle sitting in the volume mesh. Now what we want to do here is we want to change the location of that rear wing. Now the way I've constructed my geometry here, it's actually just come from triangulated surfaces, and these are all here in my geometry folder. So you can see here we have the body of the car, and we also have the wing and the supports for the wing. So what I can do very quickly and simply when I need to is I can transform that wing, and it will just move relative to the car. So let's say here that I rotate it by 10 degrees, and then I'm just going to move it back 20 centimeters along the car, and we'll just execute those movements, and what you see straight away is that the wing has a new position, it's flatter, and it's further back. And that's a very simple kind of a geometry change to make, just moving parts in my domain one relative to another. You'll notice that up here at the top of the tree though, we do have a 3D CAD modeling capability. So you can construct your CAD parametrically within Star-CCM+, and then you have the capability, for example, to vary the diameter of an inlet, or parametrically change various shapes in your CAD. In addition to that, we can also couple very tightly with external CAD tools such as NX, and we can actually parametrically change NX geometry and exchange that live with Star-CCM+. So there are lots of different ways to modify your CAD, and the one I'm showing you today is really just one example. So our CAD is moved, and all we have to do now is follow our two-click process for updating our mesh, so rebuilding our model, and then running our tests, so running our flow solver live. The first of those two steps is to update our mesh. Now, meshing in Star-CCM+ is a fully automated process. What I have defined here in my tree is a series of meshing models that are going to be used, and within that there are a set of rules. So for example, I've defined a surface size that I want to be applied near the car in order to get a sufficiently refined mesh. I've also defined that I want these 4 orthogonal layers close to the wall, these prism layer mesh, which will allow me to capture near wall gradients in the flow velocity in particular in this case, and therefore accurately to capture the aerodynamics. And in addition to that, you'll also see that behind the car we have this wake refinement in order to capture that wake flow that you saw earlier. So these types of mesh settings are all best practices, and we do really pride ourselves in offering extremely good technical support. We have a team of very experienced engineers who are on hand to supply best practices and to advise our customers not only on how to create an accurate case, but how to do that in the most efficient and robust way, so as to make the most of your computing resources. So you can see here that we have a new volume mesh now. That's updated, and you can see the new wing position is now reflected in the car mesh. So at this point we're ready to solve. What I'm going to do here is I'm just going to show you a comparison of the current flow solution with the new one as we run. So let's just pop down here and have a look at something for our test. And here you go. So on the left here we have our baseline design, that's the current results, and on the right we're going to hit the solve button now, and what you'll have is the updating flow field. Now at the moment you can see that the flow field is pretty good in terms of prediction at the front of the car, but towards the rear of the car it's not yet accurate, it's not yet looking very physical around the rear wing. That's because what Star-CCM Plus has done is it's taken the flow solution from the previous solution and it's mapped it onto the new mesh, and this allows us to converge our new simulation much faster than the previous one. And so you can already see that we're starting to get an update in the flow field. Sorry, I've been click happy there, and not just in the flow field but also in the predictions for lift and drag, which will start updating live on the screen. So what we're looking for, of course, is a low drag design that has as much downforce as possible. So you can see here actually our drag value is already decreased by perhaps 10%, although of course we still need to wait for that flow solution to fully converge before we're sure of the accuracy of that prediction. If anybody has any questions, now would be a good moment. Otherwise, I'd like to show you now how this kind of two-click process to rebuild and retest your case really lends itself to intelligent searching of the design space. So if we think about it in terms of a plot, our single simulation gives us, for one single wing configuration, rear wing configuration, it gives us the value of drag and of downforce that we're hoping to get. And of course we're hoping to maximize downforce and to minimize drag. Now if we run larger numbers of cases using this intelligent search, we come up with other alternative possibilities. And some of these and these start to illustrate the trade-off that we're making between those two properties in our car. Now there are, as well as this two-click process, there are some other things that make Star-CCM Plus very well adapted for this type of analysis. We're able to run in this type of search mode across any type of hardware that you have, whether that's local desktops or whether that's cluster cores, and the flexibility of our licensing schemes mean that it's really very affordable and practical to do this kind of study. And what we come out with is a series of these best designs, if you like, that you see here in red on the plot. These designs all provide a trade-off between drag and downforce that is in some sense the best case scenario. So if we're talking about our original track that we were thinking about earlier, we have very long straights, so we want to maximize our speed, so we want minimum possible drag. The curves in this track are fairly gentle, so we're not too worried about traction and staying on in those bends, and we're willing to sacrifice downforce in order to get a lower drag value, which means our design 75 looks like a pretty good bet. On a different racetrack though, we have very tight bends and lots of them, and we don't have those long straights, so we know that our maximum speed is going to be lower. We're willing to accept a drag penalty in order to have a higher downforce and to increase our chances of sticking on the track in all these corners. And so design number 61 is a much better option. Having run this study, we have a really good understanding of the trade-off that we're making between drag and downforce, and we're able to take our pick of the best configuration for any track that we might come across. And so, to some closing remarks. What I hope I've shown you in this short demonstration is that we can use virtual prototyping in Star-CCM Plus to gain really valuable insight into product performance, so in this case our race car performance, that we can quickly and cost effectively build, test and assess design variants, so we can very quickly and easily change geometries in our case and rerun our entire workflow pipeline really very productively. and that this easy, quick two-click process makes it very straightforward to automatically and intelligently search the design space to identify whole families of high-performance designs and really to get the best possible product. So, Star-CCM Plus, through these capabilities, allows you to drive innovation and to discover better designs faster.